Να ξεκινήσουμε, Δημήτρη. Δώσε μου το σήμα. Να ξεκινήσουμε. Okay, hello. It's a great honor and pleasure for me to welcome Professor Lykourgos Magathas, who came from Kavala to meet you and exchange ideas about artificial intelligence. The title of the talk of Professor Lykourgos Magathas is Physics Code, Playing with Physics and AI Interdisciplinary Applications. Please, Professor, thank you very much for being here with us.
Good evening. As you heard, the title of my presentation is Physics Code Playing with Physics and AI Interdisciplinary Applications. I'm a professor of Department of Informatics and Research Institute of Complexity from Democritus University of Thrace. It's a really great pleasure for me to be with you to discuss some important things that physics, technology, and AI meets the trend of next years. As you know, physics is way more than formulas. It's the story behind everything, from falling apple to the tech in your pocket. And the question is, what happens in the case that we have physics, AI, and programming? This is a real magic. Today we'll see these fields and we'll go a travel to the future. Of course, we have heard the word, the term, neural nets. What is neural net? Something that is similar to our brain. We produce this with model of our brain. Okay, it has a pointer. Okay, this is a pointer. Okay. This is the input layer, this is the output layer, and this is intermediate layer or layers, it depends. And it's similar to our brain. How you think something exactly is neural nets. Let's see something more practical. It's an example from It's an example from political system United States. You know, United States has two main political parties. Okay, a voter, this is a voter, and this is the most simplest neural nets. It has one node, 3 or more inputs, and one output. This is the most easy case for neural nets. Possibly a voter takes data from the field of economy, from social security, from defense, etc., and finally, according to this relation, something else, decide what is going to vote. Vote Democrats or vote Republicans. Let's see what is AI. AI is a branch of computer science focused on building smart systems that you can do things that normally need human intelligence. However, what is the goal of AI? Is to build machines that you can see, learn, think, or make decisions, and act just like we do. The process is this. We give data, correct answers, It depends if we give algorithms, usually learn algorithms, and finally discovered rules. This is the process of AI. And finally, of this briefly introduction to AI, we have heard about machine learning and deep learning. Both are subset of small parts of AI. Machine learning, think that you are learning to drive, and someone, you say what you have to pay attention, like signs, pedestrians, traffic lights. Deep learning, you are learning again how to drive, however, there is someone to tell you something. You drive, for example, 10 million kilometers and developing your own instinct for what matters. Let's see an example to understand what I say up to now. We will see the difference between artificial intelligence and traditional computing, different approach. We have an example where they gave us two pairs of data, square meters, and the price of a house. And they ask us something different, not these pairs. Something, for example, here give us 50 square meters, 100 square meters, and ask us to find the price for 80 square meters. According to traditional approach, we think that we have a regression line with X is price. According to this relation, the tendency is price per square meter and stable term is base price. According to mathematical relations of regression, we get this equation, and finally make the substitution. We take the price of this house. Okay, this is the traditional approach, how to make these calculations. In AI approach, we use different methods. Which is the different methods? Let's see. We use again this regression line. However, we test and go on. Trial and error is the term. What means? We use 0.5 for tendency. You remember the correct number is 2000. Okay, we use this one, tendency, and the stable term 1. We made the calculations and find for 110 meters, we found this error. We make again and again, many thousand times, and finally we'll find the correct answer, which gives us the same number for price. This is the approach according to AI. And as a conclusion, we can say that traditional computing does precisely what is introduced to do. You specified the computer to do this calculation. In AI, learns from examples and data, and this is the main advantage. Okay, there's a problem. In many times, we need to know the surface of a diagram, like VT, speed, time. We want this surface down to the diagram. For example, in the case of work and force, we want to find the work if we calculate the diagram. In sometimes there are very interesting for physics applications to find the surface of a scheme like this one. And we use AI in order to make precise calculation. Let's see the example. We put this in a rectangular. Then we place spaced points over the rectangle. These points, 1, 2, 3, 4, etc., 60 points. And then we measure the points in the area. This is the area. Okay. And we found 16 points. If we increase the frequency of data points, of placed points, for example, 105, we found 31. And using AI, do this for many other frequencies. And for the case of, for example, 1,060 points, we found 477. I remember what is this number. The total number of points and the number in these areas. Okay. The ratio of number of points in the unknown surface is 0.26, and finally, if we increase, found 0.29. And the surface, the first is a small false, the first. 16. The correct is 16. We found 0.298 multiplied with the dimension of rectangular. Before we go on, let's see what is nanometer. Nanometer is 100,000 smaller than the diameter of human hair. Let's see the scale, what we are talking about. This is a molecular of water. This is more complicated organic molecular. And here is tennis ball. Okay, tennis ball is 100 billion greater than nano. Why are we talking about? Because we're talking about nano scale for new generation of photovoltaic cells. These cells produced by thin film layers of about 100 nanometers up to 500 nanometers, the trend, the last trends. And why you use this kind of photovoltaic cells? For two reasons. First reason, less material, 99% less material, lower cost, and flexibility and transparency, that means it's more usable to everyone to transport this for every reason. This is a photovoltaic cell. Photovoltaic cell, I remember you, is an apparatus that transforms the sun energy to electrical energy. This is a typical photovoltaic cell. The orange area is the P area. Green area is, the orange area is N-type area. Green area is P-type area. And cross-sectional view is this. We decrease this height to some nanometers. Why we decrease it? Because we can do many other things with less material. Again, I say this is important. And we found something more interesting. We can produce many layers many combination of these kind of layers, and finally increase the gain of photovoltaic cells. Photovoltaic cells have now typical gain about 20%. That means 100 photons incident on a surface, you get about 20 electrons. According to the theory of materials, we can say that the most important property is energy gap, is related with material property. There are other material properties like optical absorption, electrical conductivity, electrical mobility, dark electrical conductivity, etc., where all this data provided to AI. And what happens? AI now design the material. What means design the material? You give the ideal properties in order to succeed the maximum transform of energy, and AI with robot produce layer by layer that means group of atoms deposited on a substrate, suitable substrate, and produce very thin films with special characterized properties. We can see similar application in solid-state physics, how to see invisible areas in nanoscale. Why is invisible? Because we have two kinds of microscopies. The first group is optical microscopies. What is optical microscopies? We use the light and to see a small amount of matter. However, 50 years ago, we found electron microscopy. Electron microscopy has a limit of about 2 nanometers. However, nowadays we have applications like super batteries, graphene 2D, two-dimension means 2D material, is the new generation of processors, and many applications in medicine that we need lower dimension, less than 1 nanometer. And what we do this? We provide to AI data, and AI managed to do two different things. The first is to disappear the noise. Do you know what is signal noise? Signal noise. Do you know? Okay. Here we have signal noise. And according to this neural network, disappear the signal noise, and we found this picture. Also, we increase the definition, the scale of definition. This is from electron microscopy, and this is using AI. And of course, you will ask me, is it possible AI to give results that are artificial, not real? No, completely no. We're sure about it because we pose to AI all physics and chemistry rules. This is latest picture from graphene. This is one layer of atoms that we can see using AI with high definition, without noise, and the robot system today gives exactly the conditions and produced this new material. We are talking about new kind of materials next 3-4 years. What does it mean? It means that what we have problem now, we have problem with insulators in high frequency, for example. We can produce materials with specified properties, okay? More loudly. Would you like to finish and to ask me at the end? Okay. And to see artificial intelligence and physics in medicine and pharmaceutics. Look, you know that physics has involved in imaging techniques in medicine, for example, in computed tomography scans, X-ray scans, ultrasound, etc., etc. However, using the theory of higher definition of microscopes, we can see with better possibilities problem in tomography. For example, nowadays, a tomography can find something up to 0.1 centimeter. Next generation with AI will give at least 1 or 2 orders of magnitudes accuracy. That means we can see something 0.001 millimeter or microns. However, the most important today is the involved physics in difficult problem like cancer. We use quantum dots. What is quantum dots? Quantum dots are small parcels of semiconductor crystalline atoms, about 1,000, from 500 to 5,000, that can be activated using energy, suitable radiation, and cancer cells absorb selectively this kind of parcels, and when we succeed this, at this stage, we can activate these parcels to explode. Not exactly to explode, but things like to expose. And we have this situation where we destroy all these kind of cells. However, nowadays, we use drugs, hard drugs, that disappear these cells and disappear healthy cells. This is the new technique that gives us the possibility to defeat this human problem. We can do this also by treatment using infrared light. Why infrared light? Because using infrared light is more efficiently on these cells. Finally, I can say that the future of medicine includes instant medical diagnosis, targeted therapies with zero side effects, only problematic cells, and will design targeted nanorobots for detecting points in our body that possibly these points will be a problem in the future. And of course, we have heard the term personalized medicine. What is personalized medicine? To give us AI the recipe for any kind of problem with your health. And finally, we'll talk about application of physics and AI in economy. Up to October of 1987, we used typical finance, from economic science. A big crash in finance in October 1987, we found something that is not easy to explain. What we found that S&P 500, the biggest and more stable finance index, lost 23% in one day. Many scientists from all fields tried to explain this, from mathematics, from physics, and finally, two physicists, Eugene Stanley and Madenia, found something very interesting, that statistical physics can explain this crash in finance index. It was born econophysics in 1992, 5 years later. However, the problem of econophysics is involve complicated computational and more difficult is to find the result in one day. In one day. That means I want today to know what is going to happen tomorrow or next week. This is solved by involving AI too. From 2025, we solve this problem. How, we'll see later. And the question is why we use econophysics. Why is it so important to use physics in this area? It's very, very important. Why it's very important? Because the finance markets have capitalization which is about 20 times greater than global economy. Question. Global economy. What does it mean? A small variation in financial markets could cause a great turbulence in the global real economy. For example, the Lehman Brothers default in 2008. That means a big problem in United States stock markets will give problem in Greece, in Bulgaria, everywhere. Okay, that is important to stop finance crash. The difference of econophysics and AI econophysics is the results of real time. That means we do the same, but AI econophysics offer us to find something in real time when is observed a different or something strange in financial markets. This is the big advantage. And which are the reasons we have this development of econophysics? Because we have physics theory, complex systems, financial time series, many theories of finance, computational theories, AI, machine learning and deep learning, and of course, economic data. We have the ability now to store enormous amount of data. All this gave econophysics AI. And which is the target of econophysics? The target of econophysics is to analyze the finance behavior. Second, to forecast the finance indices. And the most important, to prevent systematic crash. What is crash? Like this. Thank you. I would like to discuss some points I show you. Here.
Okay. So previously you were mentioning the application of graphene in science.
About this picture?
Yes, here.
It is graphene. Graphene.
Yes. I have been hearing about graphene for like years, about its uses and its potential and stuff, but from what I have realized is that it just keeps getting, I'd say, delayed as like applied to something that will be applied to like technology and stuff. Like, how actually feasible is it to use it in like mass scale production?
Okay, thank you. Thank you, very good question. First of all, if you have this structure of material, instead of bulk semiconductor, you save energy. What does it mean, save energy? Because an electron is here and comes from here to here. You save distance, because if the electron goes from here to here, there are many other phenomena like scattering. Scattering means loss energy. You save energy. The goal of this process is to find something to be high speed with low loss energy. Okay? Welcome. Other question? The microphone?
Okay. So, you mentioned something about quantum dots and the fact that they cure cancer cells. So, how can we be sure that they won't damage the healthy cells?
We have experience. The question here is, which is involved AI. AI involved in quantum dots in order to construct something which is specialized for specialized person. This is the involved of AI. We produced quantum dots. Of course, with AI and robot machines, we can produce many, many easier quantum dots. I'm not medicine, but if you have a problem, or if someone has a problem, this problem with other person, both of these people have not the same profile of quantum dots. AI finds the correct recipe. Okay. Other question.
I would also like to ask about the quantum dots. How can they be personalized for each person specifically? And also, do you think that quantum dots and AI are the future of cancer treatment or other methodologies like CRISPR?
Okay. From here, the cancer cells have absorbed the quantum dots. Okay, quantum dots. We activate these dots, and these dots finally show these points in these are red. From the color of these dots, you can find the type of cancer cells. The color, the different color. For example, here is red color. In some other cases, look, red color has a frequency or wavelength. You can find the exact color and you can, if applied, specified quantum dots for this color. Okay. The other question was?
If you think that they are the future of cancer treatment and not like other new methodologies like CRISPR?
Of course, I can say that is new way to defeat cancer, of course. It's a new method. I hope in comparison with nanorobots, that means we have much better or higher level of diagnosis. In comparison with this, we'll defeat this problem. Okay.
Congratulations.
Hello. If it's possible, could you repeat briefly what you said about the economic crisis and how they're predicted?
I can explain. First of all, we have to understand that we live in a world, we live in a real economy. Okay. At the same time, there is another economy greater than real economy, 80 times more. That means we are working and we produce something. If we add this production of each person on this earth, is about $110 trillion. Okay. The capitalization of finance markets, it's 80 times greater than the real economy. If we have phenomena like October 87, believe me, we live like a third world war, because a damage, so big damage in finance markets will ruin the real economy. And this is a problem today. What we have to do to detect this kind of crash of finance or end to prevent this crash? How to prevent? You have to know anytime what is going to happen. And we know, if you know this behavior, you can stop the first step is to stop all the important markets. For example, when we have global events or something that is important for the people in the big countries like United States or Europe or China, for example, something which is related with the murder of President of the United States or China. The other day, finance markets are closed. Okay. Other question?
Congratulations for your presentation. How close we are to a point where AI can replace radiologists as a science? We have heard scientists say that AI can detect breast cancer 5 years before human eye can detect in a hospital.
Okay. I can say what I feel now. I feel that the history is running with higher speed than 10 years or 20 years ago or 100 years ago. That means every day it's something new that can change everything. Think this. The total knowledge in physics is doubling each 3 years and a half. What does it mean? A student in physics department for the first semester, after 3 years and a half, when he is going to finish his studies, he has the knowledge of half of the science. And this is complicated. The second is when you are running technology, science, medicine, everything with high speed, you don't know what is going to happen next seconds, believe me. And of course, we're talking about new generation AI next year from this year. I mean that I believe that after 5 years, 4 or 5 years, will expand the life, the average life, about 20 to 30 years. This is what we expect now. Possibly in 2035, we say we can expand more than 100 years. I don't know exactly. I believe something, that the situation gives us to believe that nothing is linear. For example, we found something after 10 years. That means after 10 years we found something equivalent to this. Now we are running with high speed and we increased speed. That means we have acceleration, increased acceleration, and nobody can say safe what is going to be done after 3 or 5 years. However, I believe that we'll solve many human problems in the next 5 years.
I think we have a last question, please.
So you mentioned that you can use graphene to make high-efficiency chips for computers, but standard masking techniques like projecting light into graphene light has a too high wavelength to make so efficient chips. So will this AI be able to reconstruct the chip layout by itself, atom by atom in the graphene?
Can you repeat it, the last words?
Can this AI that helps with building graphene atom by atom reconstruct complex chip designs?
Okay. First of all, we have this technology, which is the classical technology to increase the speed of processor. And we have other techniques, quantum computing, that use other circuits, other processors to manage this. At this point, this kind of processors give us the promise to succeed what you described. I don't know exactly what is going. Now we're trying to find better processors using superconductors, using quantum computing, and using this kind of processors. Is there any other question?
Anyway, you have made the record of the question for the third Balkan Summer School. We had more than 6 questions for you. Thank you very much, Professor. It seems that you have ignited the young minds from Balkan region. Thank you very much.
Thank you for...
The next invited speaker is facing a problem right now. So, a young lady will start the presentation of the pupils. Please, I want you, Dimitrios, can you help us to put the chronometer? So the rules goes like this. C has, let's say, 8 to 10 minutes to present her study, your little project, and if there's a couple of minutes, you may answer a question for one of your colleagues or by us. You may talk. Is there any other brave young mind that want to be the next presenter? Okay.
Hello, my name is Maria Geronti. I'm from Greece, and I'm gonna present you my project on how AI helps in discovering drugs, materials, and future technologies. The first part of my project is about medicine and how AI can transform medical research from algorithm code to clinical practice. Here are the stages of developing with AI. First is the target identification. It's about deep analysis of genomic and biological data for the precise identification of new therapeutic targets and biomarkers. Then is the generative design, which is the use of generative AI for in silico design of new molecules, simultaneously optimizing efficacy and safety. And it's the virtual screening, which is a rapid evaluation of billions of chemical compounds that dramatically are reducing the cost of physical testing. The next generation clinical trials AI. It drastically reduces the overall time and cost of developing new therapies. Intelligent patient selection through analysis of electronic health records and big data. Accurate prediction of toxicity and pharmacokinetic properties before human trials, and continuous monitoring of patient progress through digital biomarkers. Here's the things that make scientists go from target to drug candidate critical stages. Identification of biological targets. First is the 3D protein structure prediction, then the generative design for new molecules with a high affinity and lower toxicity, and prioritization from preclinical and clinical studies. Why it matters. AI transfers a large part of the testing from the lab to the computer, resulting in fewer failed options and faster R&D decision. R&D is the amount of time that a company needs to think about a new product. And I have an example here is Halcine, an antibiotic discovered with the help of AI, and it's discovered by MIT researchers. It is particularly important because it can combat bacteria that have developed resistance to many existing antibiotics. The second part is about materials designing. The structures of the future, atom by atom, overcoming the limitations of human intuition. First are the autonomous laboratories that sweep vast spaces of potential composition and crystal structures. It evaluates properties such as stability, conductivity, and energy efficiency, and leads robotic labs for rapid synthesis and verification. The applications of new materials, it's the energy storage, it's the development of materials for solid-state batteries, offering increased safety, faster charging, and greater capacity. Then is the semiconductors and quantum, and the discovery of materials with superconductive and quantum properties for faster, more efficient, and next-generation computers, and sustainable techniques, the design of biodegradable materials and durable catalysts for reducing the environmental footprint. It's also known as green tech. So here are the benefits and things we should be careful about with using AI in discovering new technologies. The benefits are, of course, the discovery speed that is increasing by 90%, the reduction of unnecessary experiments that is decreasing by 80%, and better research targeting that is increasing by 85%. And here are the risks that we should be aware of. The quality of bias of data, the interpretability of models and reproducibility, regulatory framework, safety and intellectual property, and need for collaboration between scientists, engineers, and regulatory authorities. Thank you so much. Those are my sources.
Congratulations, Maria. Congratulations for the topic, for your English fluency, and most of all for your confidence to be the first to jump into the fire. Congratulations. So, now we're going to have a small break for a couple of minutes. The next presenter is here, so you may stretch it a while, and we started in a couple of minutes. Thank you.
Συνεχίζει, αλλά μισό λεπτό λίγο να το...
So in that case, I'd like to ask Dr. Alexandra Eleni Koloniari. You're a doctor, aren't you? Candidate. Okay. Okay. The topic of her presentation is Listening to the Universe with Artificial Intelligence, Gravitational Waves and Neural Networks. Please, candidate, PhD student Koloniari. Thank you.
Okay, so I hope you enjoyed this small break. Together, as mentioned, we will talk about how we can listen to the universe with artificial intelligence, and more specifically, how we can detect gravitational waves using neural networks. But let's start from the beginning. And when I say from the beginning, I mean from the very beginning. From what is gravity? So if we would ask our friend Newton what is gravity, he would say that gravity is an invisible force by which every object in the universe instantly pulls on every other, and it depends from the masses of those objects and the distance between them. And in fact, this theory is very good when we consider the day-to-day life. However, it starts to fail on specific cases, such as when we have speeds that approach the speed of light, when we have gravitational fields that are very strong, and of course, when we need to take into account the fact that changes are not transmitted instantaneously. So, is there another theory that maybe can solve all those problems? Of course there is, and is the theory of Einstein, in which we can reach when we take into account the fact that space and time are not two completely separate things, but in fact a simple unified fabric. And this fabric is generally called space-time. And I have here a figure, a representation basically of what this fabric can look like in 2D. So, according to Einstein, gravity is not a force, but it's the curvature of that fabric of space-time. And objects move by following these curves on space-time. And basically, you can see what happens in this figure, in which you can see that the more massive object, basically, around it, we can see a larger curvature compared to the other objects that are less massive. Okay, but I talked about the fabric, so you might consider that why do we talk about time anyway? When we are thinking about the fabric, we are thinking about space. Well, the thing is that time does not pass at the same rate everywhere. So where space-time is curved more strongly, for example, when we are near something very massive, such as a black hole, for example, time passes more slowly. So space and time are interconnected. And by having that in mind, we can now describe what gravitational waves are, and they are disturbances that propagate through that fabric of space-time. And they look something like this. You can see the fabric that we discussed about before, and the waves that are caused because of those two objects orbiting each other. And when are those waves generated? When something very massive accelerates suddenly or changes its motion in an asymmetric way. And there are a lot of different sources like that. For example, when we have two black holes merging, or a collision, or for example, a supernova explosion. And a very interesting fact is that this deformation that we measure, so basically the amplitude of those waves, is actually very small. It's in the order of 10 to the minus 21. So basically, it's smaller than 1,000th the size of a proton. And exactly because of that fact, although they were predicted in 1916, the first detection was actually made in 2015. And the first gravitational wave we detected came from the merger of two black holes, one with mass equal to 35 solar masses and one equal to 30 solar masses, and it came from a distance about approximately 1.5 billion light years. And of course, that was one more confirmation of the theory of general relativity. In the figure I present here, you can see some plots. The two upper plots correspond to the real data of the two LIGO detectors, the Hanford detector with red and the Livingston detector with blue. The y-axis corresponds to the time, and the z-axis corresponds to the magnitude of the deformation that we mentioned before. And in fact, the scientific term, of course, is not all that thing, but we call that strain. The middle plots that you see is what Einstein told us that we expect from two black holes with that, those sizes and that distance. And you can see that they are actually very similar, just we have some extra noise when we are actually looking at the real data of the detector. And finally, the last two plots that we are seeing are the frequency time representation, or as we usually call them, spectrograms. And what we expect to see there, if we have a gravitational wave, is that very characteristic banana-like shape, or as we call it, chirp. Here I present the current generation of gravitational wave detectors. For example, Virgo in Italy, the two LIGO detectors, Livingston and Hanford, Geo 600, and Kakrai in Japan. However, out of all those detectors, only 3 have made a detection so far: Virgo, Livingston, and Hanford. When it comes to Kagra, there are a lot of different reasons why it didn't have the ability to detect gravitational waves so far. One reason, for example, is the fact that it is placed in a mountain, and there are a lot of problems there. For example, it has a very big problem with raining, which is something that you can actually see in the figure that I present here. You can see there is a little bit of problem with the water. And also other things that have to do with the mirrors. But when it comes to Geo 600, the problem has to do with the length of the arms. So As you can see here, all the other detectors have arm length that is greater or equal to 3 kilometers. However, GEO600 only has 6-meter arms. And that is the reason why it cannot detect gravitational waves. But let's see why that is. Why does the length of the arm really matter? So here we have a very simple model of how we can actually model a gravitational wave detector. So it isn't an interferometer. We have the laser source that you can see here. So we point that laser to the beam splitting mirror, and now we have two laser beams, one that goes to one arm and one that goes to the other arm. Those beams end up in the mirrors, they return back, and they are finally meet in the light detector here. So if we haven't a gravitational wave passing at that time, the length of those arms is the same. And because it is the same, the two beams are meeting like this, so we're not having a signal. We have the same road, so we're not having a signal outside. There is no light, basically. But if a gravitational wave is passing, then we have a change in the arm length, and because of that, we have different roads for the two different beams. And that is the reason why when we have a gravitational wave passing, we will see light here. Basically, it seems something like this. Now we have the two arms being equal, but when we have the gravitational wave passing, the arm length changes, and now we have some light on the light detector. And in fact, when we have the maximum difference between the arm length, we have and the maximum light here, and also the maximum amplitude. So the phenomenon we used here is the wave interference, which is the phenomenon in which two waves meet, combine, and that causes them either to reinforce or either to cancel each other out. So a gravitational wave causes a relative change in length. And here you can see the difference in the arm length, the original length of the arms, and here is the amplitude. So for a specific gravitational wave with amplitude h, the actual change in the length is equal to that amplitude times the length. So the larger the length of the detector, the larger the difference between the arm length, so it is much easier to measure. And with that, from the first detection of gravitational waves to the present day, we now have more than 390 candidate gravitational wave events, with most of them being detected from binary black hole mergers. And here I also have a figure in which you can see the cumulative detections versus the time. The 01, 02, 03, and 04 that you see in this figure represent the first, second, third, and fourth observing period. And in fact, the sensitivity of the detectors for the last observing period, the 04, which was recently ended, actually reached approximately 160 megaparsecs, so about 500 million light years. But we actually expect it to double for the upcoming 05 observing NAD. But not only that, we actually expect even more to have even better sensitivity with the next generation of detectors. Here I have some of the main projects. For example, we expect the Einstein telescope, which will be a European next generation detector, which will be located underground, and most likely this time we'll have a triangular configuration compared to the L-shaped configuration that we discussed before, with each arm being around 10 kilometers. Although there is a discussion for alternative L-shaped configurations. And here you can see how a triangular configuration would look like. The next main project we will discuss here is the Cosmic Explorer, which will be an American detector with 40-kilometer long arms, and it will be an L-shaped. So, taking into consideration what we discussed before, since the two LIGO detectors has an arm length of about 4 kilometers, this detector will have 10 times more sensitivity compared to the LIGO detectors. And finally, LISA, which will be a space-based triangular detector, with each arm being about 2.5 million kilometers in length. Okay, so far we discussed what are gravitational waves and with what we detect them. However, we didn't discuss how we detect them. And we know that the detectors actually record thousands of measurements per second for months. So even though we would really like to just sit there and expect a gravitational wave, that is really not feasible. So there are two possible ways to search in the data. One, using classical computing, and second, using artificial intelligence. But let's start with classical computing, since it's something that is really closer to us. So when we are talking about classical computing, we need to take into account three things. We need logic, so basically we need a plan. Then we need mathematics to be used as a tool. And finally, we need a program to implement the plan that we made. Basically, it's the language with which we will communicate with the computer what we want it to do. So let's discuss the classical computing method that we are using to detect gravitational wave. This method is called match filtering, and from the first detection to the present day, it's the most widely used method for detecting gravitational waves in general. So we discussed three things, starting with logic. So let's consider a very simple idea. We roughly know what shape the signal has when two black holes merge. Einstein told us, right? So we can make a very simple plan with these three steps. Firstly, we can take the real data. Secondly, we can compare them with the template signal, so with what Einstein told us that we expect. And finally, if we find a match between those two, finally we can say that we have a gravitational wave. Secondly, we talk about mathematics. We already used mathematics because we used mathematics in order to take the template signal that we discussed before. However, we also use mathematics in order to calculate how similar the template signal is to the data at each point in time. So if a template signal matches the data very well, that means that we have a gravitational wave in the data. And we can actually consider a very simple analogy here. Let's say that we want to make a puzzle, right? The most usual way to do that is by taking the corner piece of puzzle, and then we are trying different puzzle pieces to see which one fits. So in our case, the data are the corner puzzle part and puzzle piece, and the template signals are the different puzzle pieces that we are trying to see if they fit with our corner piece. And finally, we apply our plan using mathematics by writing a program. So basically, what we do is that we let the computer to do the heavy lifting, right? So the computer takes millions of possible signals, and basically all those signals are called a template bank. Then it compares them with the detector data, and finally, if it finds a strong signal, it alerts us. And just to make you imagine how big of the work that is, if we did that for one simple signal, we would basically need some years, but the computer does it in just a few seconds. Okay, but in one sentence, what does match filtering do? Well, basically, it just slides many waveforms over our data, one by one, until one of them matches. So I've also included a visual representation here. Here in the light red, you can see the real data of the Hanford detector. In black, you can see the real signal in those data. And the blue is the template signal which we will slide over those data in order to find a match. Now that we have the template signal here, you can see that there is no match with the data. And because of that, the signal-to-noise ratio has a very small number, as you can see here. But when we finally slide that template and we finally have a match, the signal-to-noise ratio, or SNR, will provide us with a very large number. And that is exactly what we want when we are using match filtering. And if we zoom in, we will see the plots that I showed you before. But here I've also included one more very important plot, which depicts the residual. So basically what this shows is what we take if we subtract the template signal from the data. And if we have a good match, we expect that to have small amplitude and to be completely random because basically it depicts the noise. And also, finally, one very small, important information is that we do match filtering, but we applied it in multiple detectors. So finally, we would expect the same signal to appear in multiple detectors simultaneously. And that is exactly what we see here, in which we see one signal in both Livingston and Hanford detector, and you see the match. Okay, so what are the advantages of this method? First of all, it is very easy to understand. We know what we are looking for, and we know exactly why we can find it. And secondly, it is a very well-tested method. It is used for many years, from many groups, for a lot of detection codes. However, of course, there are disadvantages, right? First of all, it only recognizes signals that are the same or very similar to those in the waveform bank. And that is because we are looking for a match. So we need to have a similar signal in the data and in the bank that we are using. And it also requires a lot of computing. However, there are some disadvantages that are more important to us because we expect a lot more data now that we expect the next generation of gravitational wave detectors, right? So the first disadvantage that is a very big problem is the fact that match filtering is very, very, very slow. Imagine having to run millions of waveforms, right? And the second very important disadvantage of this method is the fact that it can miss signals that are weak in one detector because it has to apply separate threshold to each detector. Exactly because of the fact that we need to run millions of waveforms in each detector, there needs to be those thresholds in the signal-to-noise ratio in order to be able to be feasible. Okay, so is that all there is? Isn't there anything else we can try to find gravitational waves? We can just drop the subject, we can go for a gyros and just stay. Or we can try something else. Why not trying artificial intelligence? Or, since they are so trendy these days, why not trying neural networks, right? So let's start from artificial intelligence, which is the more general term. What is artificial intelligence? Well, it is the attempt to make computers think and learn like humans. And we have a lot of different goals. We want the computer to be able to make decisions. We want it to be able to learn from examples. And we also want it to adapt without us telling them step by step what to do. And that is the important difference with classical computing. Remember, in the classical computing methods, what we do, we need to create a plan and provide it to the computer. Here, we don't need to do that. And all of these abilities are actually ideal abilities that we would want from a truly intelligent machine. However, in reality, a system can still do any of those in some extent, and again, it is still considered an artificial intelligent model or code. Okay, but let's see an example to understand the difference between AI and classical computing. Suppose we want to recognize a very beautiful cat, such as the one in the photo here. Do you have any ideas how we can do this with classical computing or with artificial intelligence? Oh, I like a lot of hands. Right. Let's see. You? You can try both. One, the artificial intelligence, is one, the other, for example. Let's say. I like the way you're thinking, but if we are providing a bank, aren't we providing examples in that specific case? So maybe if we use different examples, maybe that would be a better fit for artificial intelligence. Yes? Louder? I can't hear you. Exactly. Perfect. So basically, that is one of the examples of what we can do with artificial intelligence. We can show the computer a lot of pictures and let it learn by itself. So what the other girl said could maybe work as a classical program if we could actually create a metric that we give the computer to understand the difference, maybe. But in general, if we are considering a classical program and we wanted to find if this is a cat or not, we would give it rules. So, for example, if it has ears, fur, a tail, then what you are seeing is a cat. Okay, moving on. Artificial intelligence is not a simple term, it is a family. So, the more general term is artificial intelligence, and as we mentioned before, it corresponds to systems that try to make computers think and make decisions like humans. Then, a category of artificial intelligence can be machine learning, which corresponds to ways in which computers learn from examples, without us having to tell them what to do every time. And a category of machine learning is neural networks, which correspond to computational models that are inspired by the human brain. Okay, I'm telling you this, but I want to convince you that we can have categories and that not every machine learning model or code is, in fact, artificial intelligence. So let's consider an example. Let's say that we have a computer that plays chess, or if you're not familiar with chess, tic-tac-toe, using predefined rules. So we tell the computer how to evaluate positions and moves and how to avoid mistakes. But we are not providing examples, and we are not telling it what to play. Can someone maybe say why that is artificial intelligence and why that isn't machine learning? I saw a hand there, yeah? Yes? A little louder. Very nice. Yes, that is one of the reasons. I didn't hear all of that. Can you repeat? So the prediction, basically. Yes. Exactly. That is one of the reasons we can consider this specific program an artificial intelligence. Other ideas? Yes?
With a set of rules and functions, we are told that AI learns by examples. So if we give an example, then
then this is an artificial intelligence. If we tell AI by examples how to play good at chess, then this is artificial intelligence. If we tell a machine how to play good at chess by providing a set of rules and coding and stuff, this is not artificial intelligence.
So if we are providing examples and we let it learn, then it is machine learning.
Yes, it is artificial intelligence.
The thing is that something that is machine learning is artificial intelligence, but something that is artificial intelligence isn't necessarily machine learning. Here, we are not providing examples. Yes? I saw a hand.
We're not saying exactly what it should do, so it's not like machine learning. But we're still giving it some instructions. So it is AI because, well, if we were saying exactly what it should do, then it would be classical computing. But
exactly.
Since we're not doing this and we're just giving some instructions without giving examples, it's still not machine learning and it's just AI.
Perfect. So basically, if we want to talk about machine learning, we need to have a learning process. In this specific example that I provided here, there is no learning process. We have a computer that makes decisions. It looks ahead, so it predicts. I think the girl that talked before said about that. Yes, of course.
So we move on now to machine learning, but when we take an AI model and machine learning characterizes it, how does it move on to being a neural network? I don't understand the difference between them. That's what I'm saying.
Between what?
Machine learning and a neural network.
Well, so basically, we are here. You don't understand this specific difference because now we were talking about artificial intelligence and machine learning. So basically, there is no difference per se. Neural networks is a part of machine learning. But you can have machine learning that doesn't correspond to neural networks. So neural networks have some specific characteristics. They look like the brain. We will discuss neural network later on. If you still have that question, we can discuss it. Okay? Okay, so perfectly. What I need you to keep from here is that when we are talking about machine learning, we need a learning process, right? We need examples and a learning process. Okay, so now we can discuss what are neural networks, since that was a question. So neural networks are a specific method of artificial intelligence. So it is a type of program that is inspired by our brain, from how our brain works. So neural networks, just like our brain, consist of neurons. And those neurons are simple units that receive information, they process that information, and then they send it to other units. And yesterday you discussed very analytically also the mathematics because the simple perceptron with Professor Sterioulas. Okay, and neural networks, when they are trained with many examples, they learn to recognize patterns. Now, let's see how a neural network actually looks like. So the blue circles here correspond to the input, so where we input the data. The green circles correspond to the hidden layers, so it is the part when we have the information processing. And finally, the output with the yellow circle is where the decision of the neural network is made. And here, with the hidden layers, we can have multiple layers. And the more layers that we have, the deeper the network is, and more layers correspond to more learning and to more powerful models. But so far, we're talking about neural networks, we're talking about training. So let's see a very simple example to understand why we're talking about training and what is the difference from the evaluation. So let's say that our task now is to train a neural network to understand from seeing pictures if it sees the number from 0 to 9, right? So let's go to the training part. Let's say that here I have the pixels from an image that depicts the number 6. Okay, so I have the number 6 here. The hidden layers try to understand what is happening. So let's say that the first layer here tries to find how many circles that number has. In our cases, number 6 has only one circle. Number 8 has 2 circles. And maybe the second layer could try to find something else. For example, how many angles there are in that specific number. For example, if we have the number 1, we would have only one angle. Number 6 doesn't have any. And now we have the output. And let's say that in the first try that the network sees the number 6 here, it thinks that it sees the number 8. Okay, what's happening now? That information will go back to the layers. The second layer didn't make anything wrong. Number 8 doesn't have angles, neither have number 6. But in the first layer, something wrong happened because we have one circle, but number 8, that it was the prediction of the network, has one circle. So basically, now the network knows that something here wasn't correct, and it will fix that. And we will basically do the same process again and again for all the different numbers. We will have multiple figures that we will have the same number on it, and that way the network will be trained to understand how that looks like. Finally, after a lot of tries, it will be ready. just like you will read for your exams, you will see and solve a lot of different exercises. After doing that, you don't need to read again. You can solve any exercise that I will provide to you, hopefully at least. So that is the same with a neural network. After doing all those tries, after training, now we have a neural network that knows what it does. So now, after the training, I can provide the number 6 here, and it will finally give me as an output 6. And also, just to have it in mind, we have a training data set. That training data set will not be seen only once from the neural network. Just like you are not reading your notes only one time in order to be able to perform, you read your notes a lot of times, right? And each time, the network sees all the training data set, that is one epoch. Okay, moving on. Which are the advantages of neural networks? First of all, they can detect signals that were not included in the training data set. Why is that? Because neural networks learn patterns. They are not looking for a match. Secondly, they can be improved in many ways without increasing the detection time or computational cost. Basically, we can do whatever we want during the training because we will train the neural network once. So it doesn't matter if the training will take long, because after that we can use the same network for a very small time. And now let's move on to the more important advantages, which are those that basically answer to the disadvantages of match filtering. So, once trained neural networks are order of magnitude faster than match filtering, which is again very important because we will have a lot of data now with the advancements of the detectors. And they also can detect signals that are weak in one detector, exactly because we can analyze multiple detectors at the same time. We don't need to use different thresholds for the different detectors. However, we need to be fair. Every method will have its disadvantages. For example, when it comes to neural networks, it is not easy to explain why they produce a particular result. So the reasoning is not as transparent as with match filtering. And they also depend very heavily on the training data. If the data are not large enough, or high quality, or diverse, the performance will decrease. Again, it is the same as with you when you are reading for a test. You need good notes in order to be able to perform well at the final test, right? And with that, we can now move on to our neural network, to our code, RSTW. So far, there have been 3 different models: the Virgo-Auth model, the RSTW model 1, and the latest available RSTW model 2. And here I also provide the journals in which the corresponding publications were published, the titles of those publications, and of course the authors. And each of those models did achieve its own milestone, and we will discuss all of them separately. Let's start with Virgo-Auth model. The Virgo-Auth model, like all the RSTW models, is a deep neural network, so you remember, a lot of layers, based on a ResNet architecture for detecting gravitational waves from black hole systems. Here we have something new. We have the word ResNet. So the way with which we connect the different layers create different architectures. In this specific architecture, when we are talking about ResNets, we have a neural network that uses bridges between the layers in order to be able to surpass the information without losing and by having a better flow. Let's see how that looks like, because I know it sounds a little bit confusing like that. So we have layers here. We have the 2 layers that appear here in our figure, and we have more layers here. So if we forget for 1 minute that we have this line, this connection here, what would happen in this neural network would be we have some information here, we filter that information, we pass it here, we filter that information, we pass here, we filter that information, we pass it, and it goes on. So this layer here will only take the filtered information from this layer. But by adding this bridge, or as it's called, the skip connection, now this layer will take information from both this layer and from this layer, as it is. And with that way, we can build deeper neural networks. For example, when it comes to RSTW, all the different models have about 54 layers, so they are very deep. Additionally, we are talking about a neural network. We do need to talk about the training data. So when it comes to this specific model, we did use 1 week of data, all in a time series format, and we had two types of samples, the negative samples and the positive samples. The negative samples, for negative samples, we did use 300,000 1-second segments of real noise from the third observing period. And for the positive samples, we did the same, but we did add waveforms, template signals in it. So basically, now we have a network that can see how the noise looks like and how a signal within the noise looks like. Some of you might wonder why specifically 1-second segments, why a different number? Because the more massive the two black holes are, the faster they merge. Here I have two spectrogram examples for a low mass signal and for a high mass signal. And as you can see here, for a low mass signal, we have a larger duration, while for a high mass signal, we have a much smaller duration. Specifically, we did look at black holes with masses from 7 solar masses to 50 solar masses. And for that specific range, the 1 second proved to be a very nice and comfortable duration. However, if in the future we would like to use higher masses, probably we would need to use a shorter duration. And if we would like to use lower masses, probably we would need to use a longer duration. And now we reached to the part of the first challenge for gravitational wave detections using machine learning. And here you can see the result of that challenge for the dataset with real noise. In axis Psi, you are seeing the sensitive distance, which corresponds to the maximum distance at which we can place a black hole system and still have the detection code reliably hear the gravitational waves that are coming from it. And on the y-axis, we have the false alarm rate, which corresponds to how many times the code saw noise and mistakenly thought it saw a signal. And in this figure here, the classical codes are depicted with the dashed lines, and all the neural networks that took part in the challenge are depicted with solid lines. Our code specifically is the one depicted with the purple line. And as you can see here, the Virgo model achieved the best performance among all the neural networks. However, you can still see that the best classical code that took part in the challenge still surpasses that code. So the next question is, can we outperform classical detection codes? Spoiler alerts, of course we can. And here is where RSTW model 1 comes into place. So, of course, in order to have a better performance, we would need to do some improvements, right? So the first thing we did is to expand the training dataset, and this time we did use 925,000 noise segments and the same amount of segments with waveforms. And we also did something else. We did train with a signal-to-noise ratio schedule. So what does that mean? Basically, in the first epochs of the training, we did provide only the stronger signals for the network to give. So the easiest signals to be detected. And then progressively, we did give more difficult and more difficult signals. Again, it is exactly the same as what you are doing when you're reading for a test. You start with the simpler exercise, and then you are trying the little more difficult ones and more difficult ones until you are able to solve the more difficult exercises of all. And the results were that RSTW Model 1 managed to outperform the best classical code that took part in that challenge, that used math filtering. As you can see here, the new code is depicted with blue. And it was, in fact, the first code that managed to do that. OK, so the next logical question after all that is that, OK, we have artificial tests, they are great, but what happens with the real data? Can we do something with the real data? Yes, we can. So the next model, and the one that was used in the real data, was the RSTW Model 2. And of course, we had some improvements here as well. For example, we did use a frequency filter. And why we did that? What does that mean? So basically, as you can see in the figure here, the upper plot shows in a frequency band between 20 Hz and 1024 Hz. And here you can see that the time series is very, very, very noisy. There is a lot of high frequency noise. We don't need that. The signal doesn't reach that frequency. So we can cut the frequencies and only use from 20 Hz to 350 Hz. And as you can see here, we have a much cleaner time series, and actually the signal can be, it is actually visible with a naked eye. And one more improvement that we did is that we did remove known noise glitches by using another another neural network, Gravity Spy. You can see here some glitches and how they look like in the spectrograms. Okay, we have the neural network. The neural network told us that here we have a gravitational wave. Can we trust it? That was a question today. And the answer, which was the correct answer, of course, is that we cannot trust it. And exactly because we do not trust it, we are performing different tests to be sure that what we are seeing is actually a gravitational wave. So the first test that we are doing is to see if that specific trigger of the neural network has an astrophysical probability that is greater than 0.5. The astrophysical probability is exactly what you are understanding. The probability that what I'm seeing has an astrophysical, it is astrophysical. And in order to take that quantity, the astrophysical probability, we use the distribution of the detected signals and the distribution of the noise. Another test we are performing is to make sure, if we are using, for example, the two LIGO detectors, as we did here, is to make sure that the time difference between the two gravitational waves in the detector is smaller than 10 milliseconds. And that is important because 10 milliseconds is the maximum time it takes from a gravitational wave to travel from the one LIGO detector to the other LIGO detector. So if we would see a larger number, that would mean that what we are seeing is not physical, it's probably a glitch. And the final test we did perform is to see if the residual, if there is something at the residual. So basically, after subtracting the synthetic signal from the data, is there something that remains? Before I showed you a plot, but it was a time series. Now I show you the same plot, but now you can see it in the spectrogram. So basically, here I have the signal. You can see all the noise here. And now you have the same noise, but now I did subtract the signal, and you can't see anything. So basically what we have is a nice match. And by doing all that, we finally ended up with having 8 new gravitational wave detections from RSW model 2. You can see here the spectrograms of all those 8, and here I also provide a table with the names, the GPS time, the astrophysical probability, the false alarm rate, and the time difference between the two detectors. And also I did provide here 2 examples of time series from both detectors, and you can also see the reconstructed signal and how well it matches with the actual data of the detector. And in fact, RSW Model 2 is the first neural network to simultaneously detect new gravitational waves that weren't detected by any other code ever before. Here I also provide some properties of the new gravitational wave events we detected. For example, the orange distribution, which is our distribution, actually aligns with the distribution of the previously detected signals, which is something very good. And also what we noticed is the fact that the majority of the new signals that we detected tend to have greater distances than most signals that were found in the past. And that is probably the reason why they weren't detected by the classical codes, because as we mentioned before, classical codes need to pose specific thresholds at each detector when it comes to the signal-to-noise ratio. At greater distances correspond to lower signal-to-noise ratio values. And it has been, and it still is, a very exciting journey. The 8 new gravitational wave events we discovered were the cover of the journal Hipparchos from the Hellenic Astronomical Society. Additionally, the publication that corresponds to these events wherein it is in the top 5% of all research output scored by Altmetric. Altmetric is a metric that measures how much attention a specific publication has gained. And later on, also, our new events were validated by an independent parameter estimation study, which is also good. And before basically concluding by discussing what we expect from the future and why we care about all this, I want to take a moment to say that this is our journey. So behind every new discovery, every new scientific advancement, always behind all those things that we are here about, there are people, and it's important to remember that. So this is our journey. Here, this is Parskevas Lambropoulos, Paraskevi Nousi, Evdokia Koussouba, this is me, and Professor Stergioulas. And I hope very soon to hear about your scientific journey and what you will accomplish. Okay, so now, why does all of this matter to us, right? First of all, we are pushing the technology to its limits, right? In order to measure these gravitational waves, we built some of the most precise instruments to ever be made by humans. And that is very important because all those experiments, all the science, everything returns back to society. And I will give you a very simple example. The Internet. The Internet was created in order for scientists at CERN to be able to communicate with each other. And now everyone has it and can do whatever anyone wants with it. For example, seeing TikToks all night and not sleeping. Another thing that is very important is that we are improving computers and software. For example, for gravitational wave research, as I mentioned before, we need faster and better detection codes, right? But all those codes can be later used for other applications. For example, RSW is a code that classifies between signal and noise. But we have signal and noise in a lot of different applications, in a lot of different phenomena. For example, seismic noise, medical things. So anyone could just take RSW and just training it for a different phenomenon, and it could probably use it for that. Then one also very important thing is that we are understanding our universe better. The knowledge we gain changes the way we see the world and our place in it, and of course makes our life easier. For example, without Einstein, we wouldn't have the GPS, and you probably couldn't find this place as easy as you found it, right? And finally, we are opening a new window on astronomy. Just like the telescope showed us the sky, now with gravitational waves, we can listen to the sky. And finally, I will, excuse me, and finally, we will end our talk today with what does the future hold for us in this specific field. First of all, we expect more frequent signals. With the new and more advanced and more sensitive detectors, we will detect many gravitational wave signals every day. Additionally, we will hear events that are at much greater distances from the sources that we have so far, and now they are lost in the noise. Additionally, we expect a key role for neural networks because neural networks can analyze huge amounts of data, they can work in real time, so we expect that gradually they will be in the center of gravitational wave detection. And finally, a more general point is that in the future we will not talk about AI or classical physics, but we want them to both work together. So we will have physics plus intelligent codes, so we will have more discoveries. Thank you very much. If there are questions, I'm happy to answer. Yes? Give it a second to have the mic so we can all hear.
Okay, so first of all, congratulations for your presentation.
Oh, thank you very much.
And my question is about the future observatories that you mentioned earlier.
The future of?
Observatories, gravitational wave detectors.
Okay.
Yes, and it has to do with the LISA.
Okay.
Yes.
Yes.
So, first of all, how is it going to, because as far as I know, because I've read into it a bit earlier, how is it going to keep its distance between the three spacecraft stable, since, as you said, it's 2.5 million kilometers? And second of all, how precise is this going to be?
How precise? What is going to be?
Compared to modern gravitational wave detectors, such as Virgo or LIGO.
Okay, so when it comes to how it will keep the distance, I'm not familiar with how it will keep the distance, but we expect that there will be a small difference in the length, I guess. Now, when it comes to what we have now and LISA will look for different sources. Because we have a very different arm length, we expect that it will reach different sources with in different frequency bands. So I don't know if I have it here. Yeah, so here you can see basically the strain, and you will also here see the frequency band in which each detector is sensitive, and the detectors we have so far is Virgo and you can say a LIGO that we have here. And so we are here right now. You see we have completely different frequencies. So we expect different sources here. So you can't really compare. We are searching for a different thing.
Okay, thank you. And if possible, I also have another question regarding this.
Okay.
From what I've read, this mission will launch in 2035.
Hopefully.
Yes. Considering that its Pathfinder mission launched in 2014, why will it take so long for the main mission to start its observations?
So why LISA will start then?
Yes, why will it start 21 years after its test mission, as you can say?
A lot of reasons. It's a different technology. We want to send it to space. So you can imagine there are a lot of different tests that need to be performed. Additionally, we talk about a triangular detector in this case, while the detectors we have so far are L-shaped. Additionally, we need to make tests when it comes to the data in order to be able to analyze the data that we will get, because now we have a noise-dominated data, right? With LISA, we will have another problem. With LISA, we will have basically, the noise will be signals. So you will have the signals as a background noise. So all those stuff, if you're taking all those stuff into consideration, and also probably it has to do with the money as well, or other things, I guess.
Okay, thank you.
Yes?
Can we hear the gravitational waves of the Big Bang?
Wait a minute to the mic, please, so that everyone can hear, not only me.
Congratulations for your presentation.
Thank you very much.
I'd like also to ask if we can hear the gravitational waves of the Big Bang.
Oh, that's a nice question. So, with LISA, there is a possibility that we will hear gravitational waves from very early, from the very early stages from the universe. I think there is a possibility to hear signals from the 10 to minus 15 seconds from the start of the universe. I'm not sure if that's a number, but it's something to that scale. So we will hear probably something, but that will need a lot of analysis, I guess, from cosmologists, etc. But we expect that we will probably see something from there.
We need longer detectors.
What?
We need longer detectors.
There are a lot of things that take place there, not only the fact that we would need longer detectors. I think it has to do with how you would detect something you're not sure how it looks like, and how strongly it will appear in the data if there is something in the data. So probably, I think that in the case of Lisa, the problem there would be the analysis on how to find it and not if it is in the data. I think.
Thank you.
I see one question there, I think.
Okay. I would also like to thank you for your presentation. It was really cool. Congratulations, especially the photo with the Drake. It was really cool with the gyros. So my question is more general about the gravitational waves measurements.
Okay.
What are their impact on humanity's path, science path? So how can gravitational waves measurements actually help us?
So, when it comes to the impact, there is basically no impact. As I mentioned before, the amplitude of gravitational waves is in the order of 10 to the minus 21. So, we are cool, there's no problem, don't worry. We won't have a problem with that. Now, when it comes to the impact, it's basically what I talked about here. Why does all of this matter? So, first of all, we hope, basically, we are testing for general relativity, let's say. So we're using gravitational waves to see if general relativity actually holds as it is, or if there needs to be a change, some small change in general relativity to have better results, for example. We don't have something so far. General relativity still holds as it is. But we are testing, for example, so we might have a better theory of gravity in some year, if we find something like that. Now, that is the more physical answer. The more general answer is that all the technology and everything we're gaining, as I mentioned before, returns back to us. For example, we have the lasers. I mentioned that we are using interferometers, right? And we need very precise lasers. That laser technology could then be used for medicine, for example. So you won't necessarily see it immediately, but there is an impact on society. I hope that answers the question.
What forms the gravitational waves except of the merging of black holes?
What do you mean?
How do they form?
How do they form? So basically, you have the two black holes, for example,
Yes,
orbiting.
except of the black holes.
From what other sources you mean?
Yes.
Okay, so I mentioned some here. We have black holes, we have neutron stars. We also have, okay, here. So far, when it comes to what we have detected mergers from two black holes and from a black hole and a neutron star and two neutron stars. However, gravitational waves are happening from a lot more sources. For example, a supernova explosion can create gravitational waves. Now, from other sources, probably you could say, I don't know, for example, if there are small mountains in the surface from a neutron star, for example, every time it turns, it can create something. So there are a lot of different sources. What you need is basically, as I mentioned here, something very massive that suddenly changes its motion. That is what you need. If you can find something like that, you have gravitational waves.
Okay, thank you.
I see one more question there.
You used as a metric, you used light years, and a lot of astronomers do actually use light years. But you also talked about how time isn't experienced the same everywhere. So how can light years be a stable metric for distance?
Well, when I mentioned light years, here, for example, you say why 1.5 billion years and why does it matter? Well, basically, when we have a difference in time, we need to be close to a very massive, for example, black hole, then we would have a slower time, and if we had less gravity, for example, let's say the astronauts that are in the space station do experience time a little bit differently than us, but I think it's in the matters of milliseconds, of seconds. So the difference is very small in that cases. So there is no, the distances we are talking here, for example, are so big that there's no difference.
Okay, thank you.
So, if there's no other question, we should congratulate you for so lively and
thank you very much.
amazing talk. Thank you very much. So, there is no other presentation. The second day of the Balcan Summer School is finished. The dinner will be served. It will be served at 8:30 at the restaurant. Bye.